Hello, everyone. Thanks for joining me and listening to Dr. Dongjin Zhang. He's currently a lead AI research scientist at verifiers. By the fall, he's joining Korea University as an assistant professor. He got his PhD at KAIST, the Department of Bio and Brain Engineering. And during his PhD, he did a research internship at NVIDIA, Google, and Los Alamos National Laboratory. He's leading the work on the area of Generative. Especially his papers on diffusion have been receiving many citations. I think his total citations close to 6,000 already. I think he's going to share some of his knowledge on closing the loop of alignment in generative AI. Peace, welcome.
Thank you, Professor Lee, for the kind introduction. I hope everyone can hear me clear. So today I'm going to talk about alignment. But alignment is a term that's kind of thrown away a lot these days. So we're going to start by defining mathematically what alignment means. And then we're going to discuss some main results, where I discuss results of video generation, video understanding, and closing the loop between the two. And then we'll conclude by discussing some future directions related to agents. Circa 2022, we began to see some progress in generative models with the release of GPT-3 and Stable Diffusion, etc. These models start to become kind of usable in the sense of toy models. And 3 to 4 years later, now these LLMs and generative models in general are threatening the entry-level white-collar jobs. So it's been quite a progress. But it's useful to define what generative models are. These models are trained to minimize the divergence between the data distribution and the model distribution. So basically, they are neural networks that try to emulate the data distribution. And in different domains, there are different ways to kind of factorize the data distribution in different ways such that it's much more trainable. But basically, they're doing the same thing. They're making the data distribution accessible to the neural network such that we can train it to emulate it. And for years, people in the generative AI field has been thinking of neural scaling law as some kind of a Bible. And this has been massively successful such that we started from a few tens of millions of parameters of model scale just a few years ago. And now the frontier models are known to be few tens of trillions of parameters. But unfortunately, more recently, we are seeing some diminishing returns in the pre-training, especially regarding the data wall, where we're already using almost the entirety of the web data to train these LLMs. And also, we're also seeing the energy wall because the demand for electricity is exponentially growing, but the electrical output is somewhat constant, give or take. But in the end of year 2024 and the start of 2025, O1 from OpenAI and R1 from DeepSeek appeared, and we began to see some glimpses of success in post-training. And it's known that if we have some tasks, including coding and math, where the tasks are verifiable, we can actually post-train these models to achieve massive gains in the performance. And it's known that for frontier models nowadays, almost 80% of the compute is now spent on post-training. And on top of the post-training stack, with test-time compute and harness engineering arising, we're seeing the explosion of agentic coding and these general-purpose agents, such as Cloud Coding Codex, kind of taking over the world. And so coming back to the definition of pre-training and post-training, pre-training is learning the prior. It kind of asks one thing: does the data look natural? Now, what does post-training do? Mathematically, it's defined as tilting the data distribution with the exponential of the reward function, where the reward function defines the functionality of the data. And so now you're able to ask both questions of both naturalness and the functionality. So why is alignment so lucrative? First of all, the base model that trains just the data distribution, they're not aligned with human intent. So it's not that useful when you try to interact with these base models. And on top of that, since the pre-training is so mature, if you have a way to define your reward model properly and just align it with the reward function that you want, simply sharpening the distribution already gives you very much high gains in the performance that you would like. And so we're going to come back to this diagram again and again in this talk. So it's going to be useful to define alignment in this bird's eye view. So we have a query that gets input to the generative model, which produces the response. And then we take a reward model to kind of evaluate the response of the generative model. And then if we were to do alignment on top of this, we could do steering on the parameters of the generative model through optimizers. Or we could actually do this at test time by keeping the generative model the same and steering the response of the generative model. And so there are basically two different ways to achieve alignment. One is to do this at training time. The advantage is that the compute is amortized such that it's good for deployment. So this is basically what happens for LLMs. The downside is that it does overfit to reward. So it's kind of tricky to balance between the flexibility and the alignment. For test time methods, it's useful that you can keep the base model as is and apply some reward alignment during test time so it's flexible. But again, since you have to do this at test time, it's computationally more heavy. And we are going to, by the way, we are going to talk about both ways. So that's why I'm talking about both. And I want to emphasize that when we discuss alignment, all three components matter. One, the generative model has to be good enough such that it produces plausible responses often. So I have an analogy here. If you were to make Cloud Code with GPT-2, there's no way it's going to work. So basically, the generative model has to be good enough. Now, your reward model also has to be good enough to well align with your intent. And then you need an optimizer that can guide either your generative model or your response to have higher reward. So all three components matter. And the reason why the agentic era arrived was because all three components closed. You did have a generative model that was good enough. You had a reward model for coding because it's a verifiable system. And then you had a very mature RL stack where you could apply any of these algorithms to make it better. Now, I want to argue today that that is not the case usually for video generation. And we know that video generative models have progressed a lot these days, but using these video generative models for physically plausible video generation has not been so successful. And the reason is because that we don't have a reward function that can properly evaluate if the video is physically plausible or not. This is very different from the coding approaches where you have a verifiable reward. And so this downside is known for video generative models. So in the work called SteerX, we specifically targeted this field and tried to define what a good reward model would look like. Specifically, given a video generative model which generates a video, we could use a feed-forward 3D generation network to map it to a 3D representation, whether it be a point cloud or 3D Gaussian splat. We can re-render it to the same scene and compute the consistency there such that we can maximize this consistency that would act as the reward. The good thing about this approach is that it can actually be applied not only to static scenes, but it can also be applied to 4D dynamic scenes by simply masking out the dynamic objects and applying the same thing to the static scene of the video. And now that we've defined the reward, we need some kind of approach to guide the process. And by the way, SteerX is an inference-time approach, so that we needed a process to guide the particles. And so we used SMC here. To define what this is, starting from multiple particles, we score each particle with the reward function that we designed for SteerX. And then we do a resampling procedure such that the high reward samples may get duplicated and the low reward samples may get removed. And so if we do this again and again during the denoising steps, we have the algorithm of SteerX. And what's remarkable is that after this process, we could see that not only does this process enhance the reward that we defined, it also enhances other metrics such as dynamic quality, the aesthetic quality, and even non-reference image quality metrics such as PRISC and NIQE. So SteerX, one other property of SteerX that is good is that it can be applied to any video generative model, regardless of the input being image or text, or regardless of the output being static or dynamic scenes. So this is an example of applying SteerX to 4D generation. And it's notable that by no means the definition of reward model for physically plausible generation is unique. So there could be other ways to define a reward model. So in this year, folks for Meta Superintelligence proposed another reward that defines the reward to be the negative surprise in the VJEPA2 encoding space, such that for more predictable videos, it becomes high reward. And so by defining such reward, the authors at Meta Superintelligence were able to show that even with the simplest guidance techniques, including gradient guidance and best of n, they were able to achieve state-of-the-art performance in a physics IQ bench, which is supposed to measure how physically plausible the generated videos are. And later this year from Google, people introduced another reward on top of the SteerX geometric consistency reward. They introduced this motion smoothness reward, where they define another reward to have the camera move smoothly along the trajectory. And with this reward, they again confirmed that not only does the defined reward goes up, they could show that all the V-bench metrics go up. And so in the three works that we just discussed, we were able to see that even with the simple design choices with respect to the optimizer, by defining the correct reward function, we could achieve quite some gains in physically plausible reward video generation. So we could really see the impact of designing the correct reward. And now we want to take a sidestep and discuss inverse problems. What are inverse problems? Well, they're systems that we have an unknown signal x, which goes through some imaging operator a, such that what we actually see in the system is the measurement y. And because this problem is ill-posed, there are multiple feasible solutions to produce the same y. And so because of this ill-posedness, A typical solution is to define the posterior, which is again defined by the product of the likelihood and the prior, such that if we define the right prior, we can actually sample from the posterior. And this posterior sampling is pretty much what happens if you want to solve inverse problems. And inverse problems is ubiquitous in science, especially in computational imaging and photography. And even if we just consider the linear inverse problems, there are a plethora of inverse problems, including in painting, super resolution, deep blurring, and etc. And if we also consider nonlinear ones, there are much more. And the ones that are closer to my heart are in medical imaging inverse problems. So if you go to a hospital and take a CT or MRI, you're basically always solving inverse problems. And why I discuss inverse problems is because it's a special case of reward tilted distribution. If you define the reward function to be the log likelihood, then it's basically the same thing. And so I kind of, from the bird eye view before, I kind of did a hand wavy thing and just assumed that there's a response from a generative model. But for diffusion models, it's actually a sequence of denoising iterations, such that when you have a current state, the reward is not directly defined here. The reward is only defined in the terminal state, such that if you wanted to compute something in the current state, what you would actually need is the value function. And the value function is defined by the expectation of the reward function that will be given in the terminal state. But the thing is that this thing is intractable because you would have to marginalize out all the path integrals. And in the work called DPS, we introduced a method to tractably approximate this by pushing the expectation inside. And by the way, this is a biased estimate, but this is a tractable estimate, and this has been applied to many different works. And in the original work of DPS, we showed that it could be applied to different imaging operators and such that it can be used for linear inverse problems and nonlinear inverse problems. And over the years, the field of solving an inverse problem with diffusion models has kind of exploded. And now we have a bunch of these different methods that try to approximate the same thing, but in a different way. And I also want to note that DPS, although it was originally proposed for use in inverse problems, it's being used everywhere, including the ones that I discussed earlier in SteerX and WM reward. They all do approximation the same way. And also, if we consider inverse problems in other domains, there are also other approaches. And for example, they're using DPS in PDE inverse problems. They're doing it to design protein around the site. They're also using this to reconstruct cryo-EM, the 3D reconstruction from noisy parcel data. Now, the premise of the prior approach where we used a DPS to solve inverse problems was that we knew the imaging operator precisely. Well, what happens if we don't know the imaging operator, where we can, we can design the reward model to take in both the image and the operator and to consider it in the same time to simultaneously estimate the imaging operator and the image by backpropagating it with respect to both the X and the A. And so by doing this in the work called blind DPS, we were able to show that we could estimate from the measurement, we could estimate the image and the kernel simultaneously for blind deblurring and also for other applications. And extending this to cases where we want to reconstruct a 3D volume, we were also able to show that by modifying the reward model to not only consider a single plane, but also consider the regularity along the planes, we were able to redesign the reward such that we could achieve 3D consistent reconstruction from very sparse few measurements, even when all we had access to were 2D diffusion models. And finally, we were able to show that with the same reward, not only could we simply guide the trajectory, but we could also guide the diffusion model itself online during inference such that it could adapt to out-of-distribution measurements during test time. And so by this, we could again show that from the measurements that are completely out of distribution from what the model has seen, it could actually adapt to the new measurements seen during test time and produce high-quality results. Now, all the things that I just discussed in the inverse problem part, the caveat was that they're all defined in the pixel space. And it's easy when we live in the pixel space world because the reward models, the reward functions are all defined in the pixel space. But it has to be noted that for modern diffusion models, especially the ones that target high-dimensional signals, including video, they're all defined in the latent space. So in order to compute the reward, what you would typically do is you would have to decode it into the pixel space. And if you were to, for example, take gradients, this is computationally much more heavy. And it's another problem because it introduces further approximations. And there's another caveat that I kind of brushed off, is that the two distributions that we discussed, one being where the reward model is like a generic reward, for example, aesthetics or physical consistency, they typically have a smooth multimodal distribution with modes in different parts of the distribution. But for inverse problems, if you don't look close enough, it almost seems like a unimodal sharp distribution such that you need very high guidance scales to actually push it towards the high modes. And this becomes a problem, especially when we try to solve inverse problem with latent diffusion models, because the guidance steps are computationally more expensive, but you still need iterative guidance. And the reason why I discussed this is because I want to discuss the next problem of dynamic novel view synthesis. Dynamic novel view synthesis is a problem where you have a given source video. You want to generate another video that seems like it's taken from other target views, but from the same scene. And so the reason why we want to discuss inverse problems in this case is because we can define dynamic NVS as some kind of a video inpainting problem. Where how do we define this? Starting from the source video, for example, we can use a depth estimation model to unproject it into the 3D scene. We can render it to the target views that we want to render it, such that we have videos with basically holes in it. So now it becomes a video inpainting problem. And now when people were tackling this dynamic NVS problem and in more general video inpainting problems, there were basically two paths. One was to define the reward in the pixel space, since the masks are in the pixel space. But the problem with this was that you again had to decode it every steps of the guidance steps. So it was computationally prohibitive. Now, another class of works tried to assume that there exists a latent mask that looks very similar to the pixel space mask, such that if you simply resize the pixel space mask to the latent space, this would work. Well, it's an incorrect assumption because your encoder is nonlinear. And so in the work called Inverse Crafter, we aimed to correct for the forward model or the reward model for this problem. So starting from the pixel space, our target video inverse problem, assume that there's a continuous latent mask H that is defined as follows. So if you work out the math, it's kind of trivial to see that if you wanted access to this continuous latent mask H, it's given as the difference between the encoded target video and the encoded mask target video. The problem is you don't know the target video. And so in the work called Inverse Crafter, we made an approximation that if the source video is close enough to the target video, you can simply swap X target to X source, which gives you a much more plausible approximation than simply resizing the mask, and such that we can use this continuous latent mask H to solve the inverse problem. So before, if you were to take the reward function in the pixel space, you had to decode it into the pixel and compute the reward there. Now you have an inpainting problem solely in the latent space, so you don't have to compute the decoding every time. And now, since all the process is linear, you can use any linear inverse problem methods to solve this problem in a cheap manner. And so with this simple technique, by applying standard inverse problem solvers, and in this case, we used a method called decomposed diffusion sampler, we were able to show that with the same diffusion model trained solely for video generation, it was able to solve this dynamic NVS problem in 0 shots. And what's remarkable is that since this is a very generic video inverse problem solving approach, we could actually use this to solve other video inpainting tasks, including the one that involves editing. Now, for repeatedly along the process, when we discussed reward alignment, we kept on discussing how to estimate the value function. Well, what is value function again? It's the expected reward given your current noisy latency t. And so there were basically three approaches to approximate VT. One is to use the treaty proxy or the DPS proxy that I alluded to earlier. The good thing about this is that it's computationally tractable and it's cheap. The problem with this is that it's a biased estimate. Another approach, which is computationally more demanding, but is an unbiased approach, is to do Monte Carlo rollouts. You could do that, and by setting n to infinity, yes, you get an unbiased estimate, but in practice, if you want to compute this, you have to set a finite n, which induces high variance. So this isn't too desirable at most cases. Another approach that we did not discuss is training the value function directly. And this approach has been applied since classifier guidance, but people have been kind of ignoring this path because training the value function has been very costly for a long time. And people have been trying to train the value function from scratch or trying to fine-tune a reward model some specific tasks, but this wasn't too scalable because if you needed alignment for some specific reward, then you had to train the value function from scratch, and you had to do this for every different reward functions. But what if I told you that training a value function only takes a few GPU hours? And then that would be a feasible approach. So in the work called StitchVM, we did exactly that by stitching a diffusion model with the reward function with the linear model in the middle, such that the corresponding value function contains both the ability to denoise the latency t and the ability to compute the reward function. And when we designed the value function as such, we could show that by simply regressing the value function towards the reward at the terminal state, and by the way, we can show that at the optimum, this indeed induces the correct value function that we want. We were able to show that StitchVM could be trainable in a few GPU hours. And so applying StitchVM, what was remarkable that not only was this able to accelerate the inference time guidance techniques, including DPS and FK steering, which is a representative SMC method to guide diffusion samples during inference, we could actually see improved performance because compared to DPS, this again is an unbiased estimate so that we can obtain more correct value functions, so to say. And another remarkable thing about StitchVM is that we can apply this during training time and apply it just naively to existing diffusion RL approaches, including draft and diffusion NFT. And we were able to show that the convergence behavior of these methods improve a lot. All right, so I think that was enough for discussing generically the alignment of diffusion models and flow models. But again, the title of the talk was alignment of generative models. So we do want to discuss some part of alignment in LLMs or more generically VLMs. And when we try to discuss alignment in LLMs, some of you may think that the problem is already solved since we have Cloud Code and codecs. And I would agree with you if we were to discuss the coding agents, which only involve text. But if you guys have some experience using these coding agents or more generic agents with vision capabilities, you might have seen some blockages because the video LLMs or VLMs that are behind the scene aren't as good as you might expect. And for example, if you recall the video that I showed you for introducing you what inverse problems are, I made that with Cloud Code, and it took me like 20 iterations to actually make the video plausible to humans. And so the reason why it's so hard for these agents to make good videos or good, by the way, I also made this slide with Cloud Code, and it took me like, I don't know, 50 iterations to actually make this slide. And the reason why that's so hard is because the vision agent part is broken. And I like to simplify this part by assuming that agent is a consecutive call to the LLMs. And if we simply consider coding agents that only deal with text tasks, they already have very good atomic capabilities, such that the short context tasks, they already have very high accuracy. And on top of that, for coding agents, they have a very good verifier. For example, you can simply run the code and see if it works. And that kind of acts as a reset button to the accuracy, to the errors that accumulated during the process. But for vision agents, first of all, you don't have that good accuracy even for atomic tasks, and you don't have a good verifier. So you really do need to improve the vision capabilities. And specifically, let's consider a video LLM, which takes in the frames as input, and let's consider a video of Mickey squatting. And now, if we take the raw frames, we have 9 frames. But the problem with video LLM is that the token count for these videos is very large. So even for frontier models, including Gemini, what you would typically do is you would sample the video frames in 1 FPS, and you would input the sparse frames. And even if human sees these 3 frames, we would probably think that the Mickey is squatting because you've never seen the Mickey standing. If you do the same thing, but with a different phase offset, the model now predicts that the Mickey is dancing. And if we do the same thing, but with a different offset, now the model predicts that the Mickey is standing because, again, it has never seen the Mickey sitting down. Well, what happens if we simply show the model all the frames? Now this is again a problem because it's known that for longer tasks, video LLMs are known to behave poorly, especially for dense sampling process with short videos. It doesn't understand the intricate motion that well. And if you don't have a large enough VRAM, it will induce OM. Now, again, I want to mention that it's very standard in video LLM literature that if you use more frames in a very dense way, it will actually make your video LLM accuracy worse. So in a work called video parallel scaling, we propose the following. Starting from the input video, we split this in a different way in 3 parallel streams. We take the video LLM predictions, and we aggregate them in a weighted aggregation sense, such that we can use this probability per token to estimate the next token. And so with the simple approach, what we could show was that the video LLM hallucination reduced significantly. For example, in this case, the base video LLM is saying that the parrot is attempting to participate in a human's tea drinking ritual, which might be true, we don't know, but with VPS, it doesn't start to hallucinate. This is another example. If you show the video LLM some examples of video with vehicles in it, it often simply assumes that a person rides it because of the prior that it has seen. But VPS corrects for it by saying what's actually in the scene. This can actually be seen in a more theoretical view, where we can show that in the best case scenario, where there's no correlation between the streams of each input to VPS, a term scales j times faster. By the way, j is the number of streams in VPS, such that even in a theoretical view, it makes sense that VPS performs better. And we were able to show in different model classes, different model sizes, and different benchmarks, we could show that with using VPS, we could consistently achieve better performance. And also, this is an experiment that I like. If you are familiar with test time decoding approaches, you might be familiar with self-consistency, which does majority voting with the same input. So in the single token decoding case, the only difference between self-consistency and VPS is the input to the network. So VPS sees different frames per each stream, and self-consistency sees the same frames for each stream. So in this plot, where we see that VPS strictly outperforms self-consistency, we can see the importance of using different frame subsets for these streams. Right, so all the results that I showed you before were assuming that we were using uniform weighting across the streams. Well, is there a better approach? Well, we could think about entropy, where high entropy means that your model is unsure of its prediction, and low entropy means the model is sure of its prediction, albeit it could be wrong. And so a natural approach is to upweight the low entropy predictions and downweight the high entropy predictions. So in the work VPS, we proposed another weighting approach where we used the softmax of the negative entropy such that by applying this, we were able to see further gains in the results. And this can be seen as some kind of interpolation between the uniform weighting scheme and the minimum entropy selection, such that we're selecting it softly the prediction that, that minimizes the entropy. And this can, again, be seen as defining a surrogate reward model, because for video LLMs, we don't have a closed reward model they can use, so that we kind of define the surrogate reward model that works well in practice. Now, today I discussed quite a bit about video generation, both about video generation and video understanding. So I do want to finally touch upon how we can synergistically combine these two. So video LLMs are known to have very good semantic understanding of the generic video scene, but it's not good at the intricate understanding of motion. In contrast, video diffusion models are very good at modeling the intricate motion in short videos. So what if we used a reward model as the video diffusion model and trained the video LLM using this reward? So that's exactly what we did in the work called VDA, where we took the motion features that are output of the motion encoder, projected that to the video diffusion model, and with the video diffusion loss, we could train the motion encoder such that it learns intricate motion details that the video diffusion model already has. And in practice, we could show that by doing a three-stage training approach, where we first kind of warm up the video diffusion model to understand the motion features, and then actually training the video encoder, and finally adapting the LLM to the new vocabulary of video encoder, we could see improved performance, especially in motion-centric understanding of these video LLMs, while not hampering the generic capability of video LLMs. And so we kind of discussed a lot today, but again and again, we come back to the same bird's-eye view. So in the first part where we discussed physically plausible video generation, we showed that reward modeling is a very important part of alignment. In inverse problems, we showed that devising a proper optimization method was important. And in more advanced inverse problem solvings, we again came back to the reward model design, and we showed that proper design could achieve further results even in more complex settings. And in accelerating alignment, where we showed that training the value function was another lucrative approach, we again came back to the reward modeling. And for video agents, we came back to the generative model because that was the bottleneck, that the video vision agents were not performing as well. And finally, we also discussed kind of closing the loop between generation and understanding by defining the reward model to be the video diffusion model and the generative model to be the video LLM. And so I guess we have 4 take-home messages today. The first is that alignment is the unifying lens of both training time and test time guidance methods. The second thing basically says the same thing. And for a lot of these approaches, we again and again saw that the reward model is often the bottleneck. And while we discussed the earlier parts separately, the understanding and generation, they can actually be understood in a unified framework. Yeah, with that, we do want to finally touch upon what could be coming next. And I think the same thing applies for modern agents, where we think of the agent to be this kind of harness. And now the LLM calls not just produces a single response, but it produces a chain of response. And so if we define the reward correctly or design the evals correctly, that could be another very lucrative approach. And we also do want to make way to better enhance the optimization procedure of both the VLM, diffusion models, or the harness itself. And yeah, with that, I would like to Thank you for listening, and I would be happy to take any questions.
For excellent talk. Any questions? Do we have any shot?
So, thank you for the great talk. And I was wondering, you said the video understanding test is with the LLM agent is the LLM agent is identical because the long video thing makes a contextual problem. So what if we just have the video as a file and here's a corresponding appropriate tools like video editing or video searching tool and use it to split the video or make it as extract the information and covers the context, then can solve.
Yeah, that's a great question.
For people that question.
Right. So the question was, why can't you design an agentic system where you treat the video as a file and use all these different tools, including video editing, video summarization, and all that. And if you use the right tools, can't you understand the video in an agentic fashion? So that was the question. My argument is not that we cannot use such agentic system, but my argument is that the video LLMs lack the atomic capability. Even if you just it's not that the video LLMs are bad at long video understanding, because the agents are good. But let's say you have a 2-second video where a subject is moving very fast. If you input all the frames to the video and video LLM and try to make it understand, you won't have a very good chance of making it understand, because it's not that good at the atomic capability. So that was my argument. And so if you want to build a good agentic system, your atomic capability first has to be good enough, was my argument.
Great talk, beautiful presentation. I've got
Thank you.
2 questions. So the first question is actually about, you mentioned at the end of the talk, so using diffusion model to make the VLM a little bit better. So my question is the opposite direction. So why can't we use VLM as so we want full trained diffusion model, full metric model, so that we can enable generative model to actually think and reason while drawing and generating. So, for example, how diffusion models, it denoise well, so it's learning how to denoise or how to learn the mapping function between source and time distribution a little bit better. But sometimes we can see that the image looks a bit off because it lacks common sense knowledge. So why can't we use VLM to fix that?
Okay, so the question was, why can't we use video LLMs as a reward function to train video diffusion models? It's not that I haven't thought of it. It's more in the implementation details that are harder to actually train video diffusion models with video LLMs as an explicit reward function. Now, there are approaches where we implicit alignments between the feature space of the video diffusion models and the feature space of the video LLMs. I think that's a more viable approach now, given the difficulty of the implementation on the explicit reward design using video LLMs. Because for video LLMs, if you want to use it well, you have to do an autoregressive inference, right, to do tokens. But then that would be computationally prohibitive compared to the usual video diffusion model training. And so I think a more computationally tractable approach for now is to do implicit alignment, if that was indeed what you wanted.
My second question, great work, because I did work on recently a line of different lines of work that, so since we got 1-step model, 2-step model, so diffusion format model, it doesn't need to iterate 100 steps. So we don't need X0 estimation 3D with big formula and generate, use the reward function, rather than we just denoise and make it the clean sample and then do guidance and then denoise it and re-noise it back and, back and forth. So like purify, correct, and re-noise and purify kind of thing. So what do you think about those lines?
Okay, so the question was, in the era of flow maps, is DPS relevant? My answer will be yes and no. If you try to incorporate flow maps into, let's say, inference time guidance methods, one problem, there are several problems, and this was actually known since the era of consistency models. If you try to estimate the X0 estimates, not as the posterior mean, but actual posterior estimates using, for example, flow maps, it still induces high variance because you still have to use many different samples to actually estimate the expected the value function, right? And so if you actually try it, it doesn't work as intended. So this is especially true for inverse problem solving, where, again, the landscape is very sharp, so that the guidance actually have to be very intricate. In those cases, I agree in theory that the flow maps may be very useful, and I've seen many cases in reward alignment where the distribution is smooth. For example, in aesthetics, this works, but for inverse problems, it's a different story.
Anybody on Zoom? And, yes, thank you for giving a tour of the whole diffusion model and alignment. Thank you very much for.
Thank you. Summed up.
Recording stopped.